Hello everyone, my name is Zherui Zhang. I'm from the Southern University of Science and Technology, Shenzhen, China. Today I'm going to present our work, a comparative visual analytics framework for evaluating evolutionary processes in multi-objective optimization. Suppose that you want to choose a means of transportation that is both fastest and cheapest for a trip. An airplane is fast but expensive, while a car is cheap but slow, and a train stays in between. In mathematical, we formulate those kind of problems into multi-objective optimization problems where multiple objectives that may be in conflict with each other need to be optimized at the same time. In real world, we cannot find a means of transportation that is both cheaper and faster than these common three. For these solutions, then no solution is better than them in all objectives. We call them Pareto optimal solution. And the set of all Pareto optimal solutions is called a Pareto front. In a more general case, gray points here represent the reference sets sampled from the Pareto front. The aim of multi-objective optimization is to find a set of solutions that is as close as possible to the Pareto front in the objective space. To solve the multi-objective optimization problems, evolutionary algorithm is an effective approach. It is inspired by the mechanism of iterative biological evolution. In each iteration, a new population of decision vectors is generated from old population. We call this complete loop a generation. Starting from randomly generated decision vectors, the corresponding solution set in the objective space keep getting close to the Pareto front through generations of evolutionary process. With so many proposed EMO algorithms, it is important for us to conduct comparative analysis between them. Guided by a literature review and expert interviews, we identified 3 levels of key requirements and analytical tasks on visual comparative analysis from coerce to fine. The algorithm level comparison serves as an overview. Utilizing multi-aspect quality measure, it should help analysts understand the overall performance of algorithms from multiple aspects. A more in-depth comparison can be done in the evolution level that will help analysts identify similar or distinct patterns among evolutionary processes. The detailed patterns between individual generations should be provided in the solution level, showing nuanced differences between solution sets in the objective space. We propose a visual analytics framework to support coerce-to-fine comparative analysis of EMO algorithms. The framework consists of 3 interactive visualization modules corresponding to 3 analytical tasks. Before visual exploration, a data preprocessing is necessary. For each generation, 4 distinct quality measures are utilized in our framework to cover all the key performance aspects, where HV and IGD are widely used, while MS and SP are to complement. 2 levels of similarities are calculated. Generation similarity leverages Wasserstein distance to quantify the similarity between 2 distributions of solution sets in the objective space. It is calculated pairwisely for all generations of 2 algorithms. An algorithm similarity is modeled as the distance between 2 time series of quality measure, or adopt the generation similarity between the best solution sets of 2 algorithms. After data preprocessing, the algorithm level comparison module gives a coerced overview of the relationship between different algorithms. A quality measure table itemizes the IGD and HV values. The scatter plot on the right depicts the similarity among algorithms by t-SNE projection. The generation sequence of activated algorithms can be further explored in the evolution exploration module. Time series of quality measures are displayed in line charts to illustrate the overall temporal patterns in the evolution. The timeline view gives detailed explanation of the evolutionary processes. Each row represents an activated algorithm. On the right, each scatter plot depicts the PCA projection of the solution sets in the objective space, and the gray background is the reference set. Analysts can click to select interested generations, while the summary panel on the left compares quality measures of selected generations with the best values. The generation similarity view is designed to aid analysts in identifying common or distinct evolutionary behaviors. From the generation similarity matrix, we build a KNN graph for all generations and use a stable layout algorithm to determine their coordinates. We also use the HDB scan algorithm to cluster similar generations together. In detail, the visual encodings of a generation node are as follows. The inner categorical color shows the algorithm, where the lightness represents the temporal order of this generation. The outer ring depicts the ratio of nodes from each algorithm in its KNN. The size of the node encodes the quality measure value, and the appearance of dark gray border means that the node is an outlier that does not belong to any cluster. Besides, time curves are utilized to help analysts trace the temporal sequence. In Solution Inspection Module, solution sets of selected generations can be directly compared. The selected solution sets are kept on the left as snapshots. In the main scatter plot, a contour map is drawn to reflect the density of the dots. To reduce visual clutter, a sampling method is introduced. Due to the large quantity of reference solutions, reference sets can be presented as a grayscale density map or textured gray alpha-Hall, in addition to scatters here. In the case study, a total of 36 EMO algorithms are utilized on two distinct test problems, DTLZ3 and DTMOP2. After specifying DTLZ3 test problem, we chose the algorithms with better IGD measure. Two cases of comparative analysis between algorithms are shown. In the generation similarity view, the intersection area of TDEA and FDV shows that the early generations in the FDV's evolutionary process are similar to the intermediate generations in the process of TDEA. This suggests the faster convergence of FDV. Further examining the solution sets, we find that the scatter plots of both algorithms has outlying solutions beyond the reference set area with relatively large similarity. In the KNN graph, we notice that two evolutionary processes start diverging from 50th to 60th generation. We can discover two obvious clusters A and B. Points in cluster A correspond to generations ranged from number 60 to number 100. After enabling the time curve of VAEA, we further inspect cluster B. These points match the generations from number 78 to number 83. This is consistent with the jitters in a similar range on the line charts. Further analyzing the small multiples of VAEA in the timeline view, we find that some solutions are moving towards the bottom corner at the same time that the jitters occur, and then spread away after the 86th generation, indicating an abrupt exploitation behavior in the evolutionary process. The contributions of our work is summarized below. We present a visual analytics framework for explaining and comparing the EMO algorithms, together with a suite of visualization and interaction designs that facilitates the exploration and comparison between measures, iterations, and individual solution sets. The limitation of our framework is the scalability bottleneck due to the time-consuming similarity computation, which can be mitigated by sampling only those representative generations. In the future, we intend to extend our framework to specific application scenarios instead of current abstract representation of the objective space. Besides, we will try to apply additional multi-dimensional visualization for solution sets and further investigate the tunable hyperparameters in the framework.